the director has been telephoned urgently, so we'll start. Anyway. Of course, I will say the usual words. It's a pleasure and an honor to present Professor Ramesh Narayan, who was born in India and later moved to the United States and has been at Harvard for the longest period of his own life, as he mentioned to me before, and is a distinguished example of international science. That is to say, what science should be like, that people should and will move around the world collaborating and enjoying collaborations. And this shows in the quality of their work. When I was asked to present Professor Narayan, I admit that as I'm not a great expert in black holes, I went to Google and looked up one or two things. And I've recently, our institute has been applying for a major kind of rolling grant. And in order to do this, we had to describe the number of publications of people, the usual bibliometrics. And you find that most people who have large numbers of publications are in large teams doing big surveys, and so they have huge numbers of publications. When I looked up Professor Narayan's professional CV, I found that his largest paper, his most cited paper has almost 1,000 citations, I can't remember now whether it was 2 or 3 authors. I think it's 2. And all of his highly relevant papers about the theory of accretion onto black holes are works of individuals, works of people who are creative and imaginative and create new science in that way, and are not monster groups working almost in human teams. So this is another very positive aspect of Professor Narayan's work. I won't go into this anymore. He will tell you about how you measure the spin of a black hole. I'm sure we'll find it extremely interesting.
That's okay. So it's too loud, I think. Yeah. It's a real pleasure to be here. Yeah, my voice is somewhat strong, and this thing is really strong today. Okay. So thank you very much for the invitation. It's a real pleasure to be here, and thank you, John. You made a really important point about science being an international enterprise. All of our colleagues are all over the world, and so for me it's a pleasure to come to a place like this, which I've never visited before. It expands my circle of colleagues, really, and I hope we will have some collaborations or discussions in the future. In fact, I already have several colleagues here who have interests very close to the kinds of things I'm going to describe today. I'm talking about Tariq, Jorge, Jesus, maybe others. I don't know, for some reason they're all sitting right there on the left. But those are the guys who are closest to my research interests. So I'm going to talk about black holes, specifically black hole spin. So that's the topic. And the particular kind of black holes I'm going to discuss are these black holes in X-ray binaries. So let me try to figure this out. Okay, so let me remind you, this is something, of course, everybody here knows. So a typical X-ray binary is a binary. There are 2 stars. So one is a compact star right here in the center, which is quite often a neutron star, but in several cases it's a black hole. And those are the systems I'm interested in. These particular black holes have masses in the range between 5 and 20 solar masses. There is a companion star, which is a pretty normal star. Often it's like the sun, a solar mass, half a solar mass, few solar masses. Sometimes it's a big massive star like 10 or 20 solar masses. But what's important is it's an interacting binary. The 2 stars are close together. So mass gets drawn from one star to the other, forms an accretion disk. So gas spirals in, and as it spirals in, it falls into the gravitational potential well of the black hole. So it's losing all that potential energy, becomes very hot. That potential energy becomes heat, and that hot gas radiates in X-rays. So we see these as X-ray sources. Sometimes, not always, but sometimes these systems also have jets, relativistic jets coming out, rather similar to the jets that we are all very familiar with in AGN, supermassive black holes, which also have accretion and jets. So the physics here is to a large extent very similar to what you have around supermassive black holes. But the scale is different. It's a much smaller black hole. The temperatures are different. You get X-rays, not ultraviolet. So there are those kinds of differences. Now, regardless of whether you're looking at a supermassive black hole or one of these stellar mass black holes, there is this remarkable fact, which is even given a name, the no-hair theorem. The remarkable fact is the following, that a black hole is an extraordinarily simple object. So if you've got a big black hole, however big it might be, could be 10 to the 10 solar masses or 10 solar masses, you can finally describe it with 2 or at most 3 numbers. So the numbers are the obvious ones. The mass, how much mass your black hole has got is one of the numbers you can associate. The second number is how much angular momentum. So you take the angular momentum J, total amount of angular momentum in the black hole, and from that you can define a dimensionless number called A star. So this is all the dimensions are absorbed in this quantity gm squared over c. G is the gravitational constant, c is the speed of light. And so this number A star tells you how quickly the black hole is spinning. So it's a number that goes from 0 to 1. 0 means it's not spinning at all. 1 means it's spinning at the maximum speed allowed. You can think of it as the black hole, the horizon is spinning at practically the speed of light. So that would be A star equal to 1. So there is the second number. So 1 is mass, how many grams, which determines the strength of the gravity of this object at large distance. A star is a spin parameter, which, as we will see, determines the nature of gravity near the center, close to the black hole. And in principle, you can have one more number, which is the electric charge. So in principle, you can add electric charge to a black hole, and that's one more characteristic or parameter that you can associate with the black hole. So each of these can be called a hair. So, a hair is something that has some property associated with it. So our black hole has got a maximum of 3 hairs. And in fact, I have struck out one of these hairs because we don't think electric charge will be, there can't be much electric charge on a black hole. Everything is ionized in the universe. Charges get drawn and they get, screened out. So for our astrophysical black holes, in fact, we only have to think about 2 hairs, mass and spin. And obviously, if an object is as simple as this, and mind you, I'm not saying that this is an approximation. The theorem says that if you really have a black hole, at least at the level of classical physics, there are only 2 numbers you can associate with it. Everything else is determined by these 2 numbers. It's quite a remarkable statement. So obviously, we want to go and measure these parameters, right? Mass, I won't say very much about it because some of the heroes in this business are here, sitting in the left of the room. How to measure mass. I'm going to talk about spin because this is a newer game, something that has finally become possible only in the last few years. And I'll tell you how far we have come measuring the second parameter of a black hole. So people like, Jorge and Tariq and others, and people in my institute and all over the world, they have gone around measuring masses of black holes. Basically, what you do is you go look at one of these binaries, watch the motion of the companion star, because this is a binary, it's going around. So you measure the dynamics of this object, and from the dynamics, as you know, just applying Newton's laws, you get some information on the mass of the black hole. It's a little bit more complicated than that, but I imagine that you have heard about this quite a lot from the people, experts here. This is where we are today in terms of what I would call believable, dynamically determined masses of stellar mass black holes. This is a more or less complete table of all the objects, X-ray binaries with black holes. These are the estimates of their masses. A large fraction of these systems are in our own galaxy, of course, but there are some that are in neighboring galaxies. There's LMCX1, M33X7, LMCX3. So there are a few of these systems which are in neighboring galaxies. But these are all black holes. They all have fairly large masses. And as you know, masses like this are too large for these objects to be neutron stars. A neutron star has a maximum mass of about 2 or 2.5 solar masses. These are all definitely much too large. So they're all, bona fide black holes with reasonably accurate mass determination. Some of them are not very well determined. Now look at this. All we know is that it's greater than 2.2 solar masses. On the other hand, you can even have a system like M33X7, which is a megaparsec away, but we have a good enough mass determination that we have a plus minus 10% error on the mass. So it's a variable bunch of measurements, but this is the state of the art today in terms of masses. So it's one hair, right? Out of the 2 hairs that we are looking at in a black hole, 1 hair is taken care of by these measurements. It's a lot of hard work, but it's a developed technique that's been applied now for a few decades. So now the question is, what about I'm pressing the wrong button here, sorry. Looks like this is not going in either direction. So let's go to the second hair, the black hole spin. So since there are only 2 hairs associated with the black hole, so as an object in physics, obviously the spin is as important as mass. And in fact, some people will tell you it's even more important, because mass just tells you how big the black hole is. It's just a scaling parameter. Spin really has a qualitative effect. As we will see, it changes the nature of space-time near a black hole. So you can almost say, if you had to choose only 1 hair to measure, the spin might in fact be the more important hair, the one you want to measure. In any case, since there are only 2 of them, you want to measure it as a physicist. But of course, I don't need to tell you that as astrophysicists or astronomers, we all know, black holes are very important. They have so many different phenomena that we observe. Surely the spin must have an effect on things that we observe. And this is the one that people have speculated about for decades now, that the relativistic jets are somehow associated with spinning black holes. That the black hole spin is what is providing the power to produce these jets. And so, it would be nice to go and measure black hole spins, see how they correlate with jets, try to understand the physics of jets through observations. So that's certainly one of the motivations for measuring spins of black holes. But people think that spinning black holes might be related to gamma ray bursts. Certainly, if you can measure the spin of a black hole, you can say something about the angular momentum of the progenitor star. As you know, angular momentum evolution of stars is very poorly understood, especially in the interior. By making these measurements, you might get some clues. Nowadays, of course, people are interested in gravitational waves from compact objects. Spin makes a huge difference. And of course, coming to supermassive black holes, we believe that they will be spinning, and people are confident that those spins have information about the whole galaxy merger history. As you know, when galaxies merge, the black holes come to the center and merge, and they remember the history of that merger, the individual spins, the orbit, etc. And if we could only measure spins of the supermassive black holes, we will have additional information on the whole history of how structure is formed. Okay, so how do we go and measure spin? The first point I would make is it's hard, and that's why nobody has done it yet. And the reason is not very hard to understand. Mass is something, mass has a long-range gravitational influence. For instance, in Newtonian physics, this mass is, this gm over r squared is a gravitational force. And this is why you can look at an orbit of some very distant object, and you can measure the central mass. That's how the masses are measured. It's a long-range interaction. Spin has a much shorter range influence. So if you have to go close to a black hole before you can feel the effect of the spin, influence falls off as a larger power of r. The force due to gravity goes like 1 over r squared m, spin goes like 1 over r cubed or something else. So what we need to measure spin is not a companion star at some large distance. You need some test particles very close to the center, which are going around in an orbit, and then you want to measure the orbit and say something about the spin. And the only test particles we have are these gas particles in the accretion disk. So if you want to measure spin, the only way you're going to do it is by having some little test particles right near the center in this case the accretion disk, look at the radiation from this accretion disk, model it to the best of your ability, and as part of that model, determine the spin parameter. Now, there are a number of ideas that people have come up with for measuring black hole spin. I'm going to talk about one method. That is the first method here, by fitting the X-ray continuum spectrum. This is a method that we have developed at the Center for Astrophysics with my colleague Jeff McClintock. I'll describe this method in detail. And it's produced results for 9 objects so far. I'll show you the results. There is a second method that has also been developed, which has been producing results using the broad iron line at X-ray wavelengths. I won't say much about that. And I'll say even less about the third method because this hasn't yet actually developed. It's a great idea. It's something that will develop in the future, but I put the question mark to show that there are no results yet because it hasn't yet come to the point of providing results. The team that has done the work I'm going to describe is something that I've been leading with Jeff McClintock at the Center for Astrophysics. So Jeff is an observer. I'm a theorist. So we have a nice collaboration. It's worked out beautifully. This is one example where I don't think either of us could have done this by ourselves. This really required very close interaction between theorists and observers, and lots of course, young people, and not so young as well. Ramesh is not that young, or Mark Reed, but anybody will collaborate with us, and I hope we'll get a few more to join our group because we can use all the help we can get. As you'll see, it's not easy work. There's a lot of things that need to be done to get reasonable spin measurements. So I'm going to give you the physics behind the method. Then I'm going to give you a qualitative idea of how we actually make it work. I'm going to show a fair amount of data. And then hopefully, in a reasonable time, I will wrap up the talk. Okay, so that's the plan. So the key physical idea is this concept of what is called the innermost stable circular orbit. So this one, let me just spend 2 minutes talking about it. So in Newtonian physics, which is what we all learn as undergraduates, if you have a point mass and you take a test particle, you can put that test particle in a circular orbit at some radius, and you know how to calculate the velocity and the period and all of that for this test particle. In Newtonian physics, it doesn't matter at what radius you put your test particle. You can always find a circular orbit. There's a simple equation, g(m) over r squared is equal to v squared over r. You solve, and you get all your solutions. And the point is, it doesn't care where you put the test particle. In general relativity, this is not true. A black hole is a relativistic object. You have to use general relativity to figure out orbits. And in general relativity, you cannot put a test particle anywhere you please. And you can almost see that that has to be so, because if you do the Newtonian solution and find out what is the velocity for a given orbit, as you know, the velocity keeps increasing as you come closer to the center. And you know that velocity cannot go greater than c. So clearly, if Newtonian physics says such and such orbit should have a velocity of 3c or whatever, clearly relativity is going to change the answer. And the way it changes the answer is very interesting. If you take a black hole and put a test particle in circular orbit, at large radius, it looks just like a Newtonian orbit. It's obvious. As you come closer and closer to the center, it starts deviating from Newtonian solution. And finally, you come to what is called the innermost stable circular orbit. If you try to go inside of that, you cannot put a particle in circular orbit. It's not as if the velocity is different. There is no orbit at all allowed. If you try to put something in a circular orbit, it will be unstable. It will either fall into the black hole or run away or do something. It just will not sit in a circular orbit if you're inside this ISCO. So it's a very, very definite prediction of relativity. It's also a very characteristic radius. If I know a given mass, black hole, and spin, etc., there is one radius. Inside of it, there are no circular orbits allowed. So this is called the ISCO, innermost stable circular orbit. And the radius corresponding to the ISCO is called r ISCO. Okay, so that's the concept. Now let's go to the main result we need. This radius, the radius of the ISCO, it turns out, depends on the spin. It depends on the mass as well, okay? So in fact, it's proportional to mass. But if you scale out the dependence on mass by looking at R ISCO over M and plot that versus the spin parameter, it turns out there is some dependence. So if your black hole is not spinning, the ISCO is at 6 gm over c squared. If it is most rapidly spinning with a star of 1, it is at 1 gm over c squared, and the thing is monotonic in between. So this is beautiful. There is a parameter, a property of the black hole, namely the position of this ISCO, which is a function of the spin. So for instance, suppose you had some method by which you can measure the position of the ISCO. So let us say it turns out to be 3 gm over c squared in some particular system. You just go look at this curve, find out what the spin will be. So in this case, it's 0.8 or something, 0.795. So it gives you a handle. If you have some method of measuring the position of the ISCO, and you already know the mass of the black hole, then you're in business, you've got the spin parameter. And more or less, every method that anybody has developed for measuring black hole spin ultimately depends on this diagram. The fact that there is a monotonic dependence between the ISCO position and the spin, and also the fact that it's quite a large variation. It's not a small 10% effect. Look at this. It goes from 6 to 1. Factor of 6 change. So, you know, with the precision that we can achieve in astronomy, this is doable. And I'm going to convince you that we can do it. So all we do is we go and measure the position of this guy. I won't spend time on that. So how does it actually work in practice? So this picture gives you the qualitative idea. So what do we have? We have an accretion disk, right? So you've got this black hole. Mass is being introduced on the outside, goes into orbit, and then it's slowly spiraling in. So your mental picture of an accretion disk should be blobs of gas which are going on more or less circular orbits, and slowly they're sliding further and further in through viscosity, right? But it's essentially circular orbits with a very small spiraling in motion bringing you to the center. You need circular orbits in order to have an accretion disk, obviously, because your gas has to go on a stable circular orbit. So what happens in practice is you will introduce gas at some large radius. It'll go around. It'll keep coming to the center until it hits the ISCO. And the moment the gas comes to the ISCO and tries to come to a smaller radius, suddenly it finds that there are no circular orbits available. And at that point, the gas will just plunge into the black hole. Okay? I guess I should make one point I forgot to mention. The ISCO is not the same as the horizon. So for a non-spinning black hole, the ISCO is at 6 gm over c squared, whereas the horizon is at 2 gm over c squared. So there is this kind of black zone in the middle where you are outside the black hole, but inside the ISCO. And in this region, you don't have an accretion disk. All you have is gas plunging in. Just it falls in on a dynamic free fall into the black hole. Outside the ISCO, you've got an accretion disk. Furthermore, as you know, the radiation comes from the gravitational potential energy that's released as the gas falls into the center. Most of the energy is actually released near the center. That's where the potential well is deep. So in fact, the disk is brightest near the inner edge, and then it becomes very dark the moment you cross the ISCO because there's no more disk there. It's just falling in. So this is the mental picture you should have. A bright ring which is producing all the X-rays you need with a dark hole in the middle, and the size of that hole depends on the radius of the ISCO. If you have a non-spinning black hole, this black region in the center will be large because the ISCO is large. If it's a rapidly spinning black hole, it will be a very small patch in the middle. And so if you have some way of measuring the radius of this dark region, or equivalently, if you can measure the radius or area of the bright region, which is what is radiating towards you, and if you have a model, you can then use it to determine the radius of the ISCO. This is the idea. So what I'm going to show you is how we do it. We will use X-ray observations to get some information on the area of this region. From that, we'll get this radius. We'll divide it by m, put it in that plot, and get the spin parameter. So, one obvious point is we don't have images of our accretion disks. Right? I mean, these are little black holes. You can't resolve anything. All you get is the total spectrum and radiation and the photometry of the object. From that, you have to get a measurement of this radius. And just to give you a qualitative idea of how this works, I want to remind you about how, this is something we all learn in the first course we do in astronomy, an easy way of measuring the radius of a star. So if you've got some star in the sky, as you know, stars produce black-body spectra, or almost nearly black-body spectra. So let's model it as a black body. Then, if you can measure the flux of radiation that you see from the star, and from the spectrum, if you measure the temperature of the radiation, there is this nice little relation. The luminosity is 4 pi d squared f, where d is the distance. It's also the area of the star, surface of the star, 4 pi r squared times sigma t to the 4 from the Stefan-Boltzmann law. And so you have this relation, which I'm sure you're all very familiar with. The solid angle of any star in the sky, which produces black body radiation, is given by this formula. Pi flux divided by sigma t to the 4. Pi and sigma are constants. F is something you can measure. That's the flux with a photometer. T you measure with a spectrometer, just fitting it to a black body. And so you directly get the solid angle of the star. Very straightforward. Then to get the radius, you need a distance. So then once you know the distance, you can get the radius. This is what we do for our X-ray binaries, except we do it in X-rays, not in optical wavelengths. We measure the flux of X-rays that we receive from the accretion disk. We measure the spectrum and fit it and get a temperature. And from this, we get the solid angle, effective solid angle of the radiating region of the disk. See, the disk itself is huge, okay? But most of it is producing infrared, optical, etc. We are not measuring that. The real action is all in the middle, right here within a factor of 2 in radius. That has a certain effective area. That effective area has a projected solid angle. And that is directly obtained by just measuring these two quantities, X-ray flux and X-ray temperature. From the solid angle, you can get the area by knowing the distance. So you have to go and somebody has to measure the distance to the object. You also need the inclination because, this is a disk. Depending on the inclination, you have to make a correction for this, this elliptical distortion of the shape. So you need to know the inclination, which again somebody has to measure by going and making measurements of the binary. Given those two quantities, we will get the effective area of this radiating region. Then we have an accretion disk model, which allows us to relate this effective area to the area of the dark inner region, and finally, the radius of the ISCO. Okay, so that's the idea, and I'll show you how it works. One point I should make is, as you can see, it's not just X-ray data that is enough. X-ray data will give us the solid angle. That's easy. All you need is X-ray data. But to get this quantity A star, you need all this additional information. You need the distance, you need the inclination, and you need the mass of the black hole. And these are all things that can only be done in the optical infrared. So, I think I will spend a little more time on this as I go along, depending on the time, because I think this might be of interest to several people here in the audience. Okay. So that was a simple idea. Obviously, that's just a schematic. You have to do the things in detail. I'm not going to load you with a lot of details. But I'm sure many of you are wondering, this all looks, very qualitative and fluffy. Can this really produce numerically solid results? So I'm going to convince you that, yes, it can produce results, and I'll show you the results. First thing is, as I've already said, we need these quantities, D, I, and M. And this is feasible. People here, in fact, do this kind of work, and our people also do this kind of work, and I will show a little bit how it is done. We need a good model. This is crucial, right? All we measure is some X-ray emission. It's the model that then goes and tells us what is the radius, what's the area, etc. And some of you might have heard that accretion disk theory is a messy business. You cannot do anything quantitative. Not true. Sometimes it is true, but not in this problem. And I'm just going to show one slide with equations here, okay? But this is the basic stuff that we all learn when we learn accretion disk theory. I just pulled out these equations from the book by Frank King and Rain, or the review article by Pringle in Annual Reviews. Anywhere you go, you can look at this. This is the famous Shakura-Sunyaev model of a thin accretion disk, okay? You're all familiar with the fact that Shakura-Sunyaev introduced something called alpha viscosity. It's a parameter, and for long, people really didn't know what's the value of alpha. And it's this alpha that has given disk theory a bad name, because people say, look, I don't know what alpha is. Why should I believe anything? What you might not have noticed is that there are some parts of the theory that don't depend on alpha. And the parts that I require for measuring black hole spin do not require alpha. All I need is, what is the luminosity of the disk? How does flux vary with radius? What is the temperature of the radiation, black body temperature of the radiation? So these are the equations that are relevant for computing these quantities. And I just want you to look at them. They involve things like the gravitational constant. They will involve the Stefan-Boltzmann constant. They involve pi and almost nothing else. Everything else is really measurable quantities. There is no alpha anywhere here. Alpha comes in for certain other quantities that sometimes one is interested in, but for this business, alpha is not relevant. So I want you to keep this in mind, that we are using the most robust features of accretion disk theory, namely just the shape of the flux versus radius, as given by just, ultimately all you're doing is you're converting gravitational potential energy into radiation. We know how to calculate potential energy. Right? That is very, very robust. It's all the viscosity that is complicated, but it's not needed for our purposes here. However, this is a Newtonian theory, okay? Shakura-Sunyaev did the Newtonian version of accretion disks. What we have to use is the general relativistic version, which is the theory developed by Novikov and Thorne. Same year, 1973. This is the model that we actually use. So this model actually says flux as a function of radius has a shape similar to the Shakura-Sunyaev, but this is the relativistic result. And it varies with spin, as you would expect. For a non-spinning black hole, the disk terminates at the ISCO, which is at 6m. For a rapidly spinning black hole, it terminates again at the ISCO, but now it's much closer to the center, closer to 1m. And so as a function of spin, you get different profiles, and this is what you fit to the data, finally, to get the answer. There is more relativity you have to worry about. You have to do all the ray tracing, and there's a lot of technology. Very straightforward, well-defined, but it has to be done carefully, and that's what has taken us a lot of the time. The other thing is, we are going to use the spectrum to get a temperature. This works only if your object is, it works best if it's a perfect black body, or if it's a modified black body, you should be in a position to compute the modifications, the deviations from black body. Fortunately, our black holes, some of the time, not always, but some of the time, go into something called the thermal state, or thermal dominant state. And this is a nice Blackbody-like state where we believe we can do the spectrum quite reliably and do the second part of this formula. If you remember, I need both the flux and the temperature. The temperature will come from the spectrum, and this is a part that seems to be in reasonably good shape. I won't go into the technical details. There's a lot of stuff there, but let's leave that aside. Let me show you some data. So here is one of our black holes. This is actually a black hole in the LMC. It's called LMCX3. This is some X-ray data collected by Beppo-Sachs. This is EFE, or nu-F-nu, versus photon energy. And these are all the data, all that coming down here, etc. This is the component that we are trying to fit. This is where most of the energy is coming out. This is a nice, smooth, Blackbody-like component. It's really a multicolor black body, but that's technical detail. This system also produces some extra emission at the level of 2 or 3% at high energies. This is what is commonly called corona. This is some optically thin Compton emission above the disk. We don't know how to model this, okay? So in fact, we just model it typically as a power law or some quantized component and just eliminate it from the model fit. But the beauty is, this is only a small contamination. So this is where the dirty aspects of accretion disks are coming, part that we cannot model precisely. So we only pick systems in which this component is a small fraction. In this case, I think it's about 2%, so it's very small. The rest of the spectrum, where 98% of the energy is coming, is fitted to this disk model. It's got two parameters, basically like a flux and a temperature, or an accretion rate and a spin. It doesn't matter. There are two parameters you are trying to fit. And in fact, there is a third parameter, which is the absorption. Soft X-rays are always absorbed by interstellar hydrogen, so that's the third parameter you need to fit. But basically what I'm trying to tell you is, you have maybe 100,000 photons here, maybe more, and you're fitting 3 numbers from it. Okay, so it's a very, very robust business. You can't get it wrong. The model you can question, but the data fitting is actually quite an easy business, and the X-ray part, if you have good data, is no problem at all. Here are some results on LMC-X3. And I'm just going to focus on the bottom panel here. This system has been observed by every X-ray satellite for eternity. And there are literally hundreds and hundreds of observations, independent observations. So this particular figure includes 403 observations. Okay? So out of all the data that's in the archives, student Jack Steiner picked 403 spectra that happened to be in this black-body-like state. Then he went and fitted each one of those 403 independently with the model and calculated the spin parameter, or equivalently calculated the position of the ISCO. So there are 403 dots, I believe, in this diagram. And what is shown here in the vertical axis is the position of the ISCO in units of m. In fact, there are multiple satellites here. It's not even a single satellite. So, there are 7 satellites. All of them give you exactly the same answer. And as you can see, this beautiful consistency of all of these measurements, I hope it gives you some confidence that this method has got some value. Okay? So all of them basically tell you that the ISCO is at approximately 4m for this particular object. What we found really encouraging was that 7 different satellites gave the same answer. Because in X-ray astronomy, there is this business about calibration of satellites, and each is a different instrument. It's a different technology even very often. And you never know whether they've all calibrated them well. Apparently they have, at the level we need. To within a few percent, they all seem to be calibrated correctly, and they all give you the right answer. Okay, I'll show you one more object, XTE-J1550. This paper was just accepted only 2 days ago. So here, for instance, are 2 X-ray spectra of this guy. One is in this thermal dominant state. So here is the spectrum. This is the part that I said we just model as a power law. We don't care. It doesn't at all bother the fitting of the rest of the spectrum. This is the part that we fit. This is another spectrum in what is called the steep power law state. It's a slightly more difficult state because there is more emission coming in this power law. But it turns out that this guy also gives pretty good results. I'll show you in a second. So these are just 2 examples of objects, of spectra for this object. So in this case, we have 60 spectra, all plotted here as a function of luminosity. Doesn't matter. All of them are giving pretty consistent results for the position of the ISCO or equivalently for the spin. And I just want you to look, all the X's are the so-called the best data, the thermal data. These other symbols correspond to these SPL data, which we think are second quality. They are not the best quality, but what we found was that they give equally good results, practically. And the whole thing is quite consistent, and you get some result for the spin. This particular object, it turns out that we were able to apply both methods to measure the spin. So we did our continuum-fitting method. We also did the iron line method using Rubens Rice, who's a student of Andy Fabian in Cambridge. So he collaborated with us. And it turns out that the two methods give pretty much consistent spin values. So from our Continuum-Fitting, we got spin in the range 0.8 to 0.54. Iron line was 0.33 to 0.7, and you get some more or less consistent results. I want to spend a few minutes to emphasize that while I've talked about X-rays, and a lot of our work has been on the X-rays, the optical and ground observations are absolutely crucial. Without it, we can't do a thing. The reason is we need estimates of mass, distance, and inclination for every single system. We also need good X-ray data, of course, but we need these guys. They come only from optical IR and, in some cases, radio observations. So I'm going to quickly go through a couple of sources just to give a flavor of the kind of observations that are required for doing this kind of work. So I will talk about this object, LMCX1. We published our results on this 2 years ago. So there's a paper, Oroz et al., in which we showed how we measured the mass and the inclination of the binary, and then the spin measurement was in Gao et al. So what do? We go and look at the companion star. So you've got a black hole and a companion star. LMCX1 happens to be a so-called high-mass X-ray binary. So the companion star is a big, massive object. It's an O star. So you go and look at that O star. So even though it's an LMC, you can observe it and do some, pretty good measurements. The kinds of measurements you do, you look at the spectrum, and you get a kind of a detailed spectral type. Specifically, you try to get the effective temperature of the star and the gravity, which comes from the, by looking at all the spectral lines in the spectrum. It's kind of the starting step, just to know what the properties of your star are. Most important, you need to know the velocity. So you need to do Doppler measurements of the companion star as it goes round and round in the orbit. So as a function of orbital phase, you measure velocities. This is the kind of stuff that, Jorge here does. In fact, this is beautiful measurement that he did of V404 SIG, famous black hole many years ago, Cazares and Charles. So, you can find curves like this. So this is very important. You need to get good dynamical information, fit it to an orbit, and get the amplitude of this velocity variation. Then, it would be nice to get some information on the rotation of your star. The lines in the stellar spectrum are rotationally broadened. Right? If the star is spinning, this side is coming towards you, this is going away from you. So the line is, apart from its own natural line broadening, will have an additional broadening due to rotation. So that if you get good data, so in this particular object turns out 4 of the lines, all helium lines, you have good enough signal to noise to actually fit it and get some rotational broadening information. That gives you what's called V sin I, rotational velocity multiplied by sine of the inclination. So you fit it and you get some number. Then you also go and measure so-called ellipsoidal modulation. As the star is going round in its orbit, its apparent magnitude will go up and down. This is because the star is distorted. I don't know whether this movie is going to show it. Right here is my companion star, which is unusually dark for some reason. Because I can tell you, LMCX1 is a big O star. It's not this dim. It's a big, bright, 30,000 degrees T effective star. So, but still, hopefully you'll get the point here. So this is the companion star. So when it's, let's just wait a second. When it comes here, its cross-section is essentially circular. This star is elongated because of the gravitational interaction, but when it is in this position, it is circular cross-section. Here you see an ellipse, here you see circle, ellipse, etc. So whenever it becomes on the side, elliptical shape, you get more radiation because there's more surface radiating towards you, whereas when it's like this, there is less area pointing towards you, you get less radiation. So in the orbital phase, when you plot the brightness, it will go up and down, up and down, up and down. So that's something that you want to measure. So here are some data on different optical bands. So this is actually quite important. It is this modulation amplitude that finally tells you what the inclination is. As you can easily imagine, If it is face on, you get no modulation. If it is edge on, you get maximum modulation. And so from the amplitude of modulation, you can get information on the inclination. So you put all of this information together, quite a lot of observations, and then you do an analysis. And out will pop out numbers that are of interest to you. So for instance, Oro's got for LMCX1 a mass of 10.9 plus minus 1.4 solar masses, inclination of some 36 degrees. Distance is known. That's the beauty. LMC, we know the distance already, so we didn't have to go and measure it separately. But the 3 key parameters we need are all available. Then you go fit X-ray data with that information, and you get some information on the spin parameter. One more example, very quickly. Cygnus X1, the most famous of all black holes, the original, granddaddy of them all, the first stellar mass black hole ever discovered. We have just finished a study. There's one paper describing how we got the distance, one paper on the mass and inclination, and one paper on the spin. Very briefly, distance is obtained in this case using radio VLBA. It's beautiful. This guy is a radio source. You can use VLBA and do direct parallax. It's just wonderful. You just observe it over a period of time, and as the Earth goes around the sun, this guy moves in the sky. You just do parallax, and here are the parallax data, 2 reference stars. You look at the east-west, north-south motion, etc., and you get a lovely 6% measurement of distance. So we now know the distance to Cygnus X1, exquisitely precisely for the first time. Then you go do all of the other stuff I told you. You measure rotational broadening, you measure the ellipsoidal modulation in the U band, B band, V band. This is the velocity variation. These have all been, these are old data. They've been collected over many, many years. But now you put it all together along with the new distance data that we have collected. At the end of the day, we have some information. So here is our best estimate of the black hole mass. It's larger than people used to think. Generally, people have assumed it's about 10 solar masses, but our estimate now is it's closer to 15 solar masses. Cygnus X1, some inclination, etc. And then you get a spin, and it turns out there is some spin that we get out of the sky. So let's not go into the details. These are the results that we have as of now. We have measured black hole spin, we and others, for 9 systems. This is the whole list of 9 systems. I have ordered them in order of increasing spin value. So this A star parameter goes all the way up to practically unity. So GRS 1915, which is a famous micro-quasar, we estimate has a spin that is practically unity. It's greater than 0.98 according to the analysis. Cygnus X1 is also up there. I don't think we know yet the final answer. We're still just polishing up the last few bits of the analysis, but it's going to be probably greater than 0.95. That's my guess. LMCX1 I showed you, that was a 0.92. And then there are a whole lot of guys at intermediate spins, and surprisingly, several with quite low spins, 0.1, 0.2, 0.3. I would say that was a surprise. I was actually expecting all of them to come near the maximum. The idea was, all stars are spinning. When they collapse, just conservation of angular momentum will spin up the object so much. I expected all the black holes would be near 1. But in fact, it looks like they're all over the place. So what do these numbers mean? I'm going to show you only one answer, or half answer that they've already given before I finish. But first thing I want to tell you is, just look at the values. Theory says A star should be between 0 and 1. And we're getting values between 0 and 1. As I said, I'm surprised that it's the whole range. But the fact that we are fitting within the allowed range, we didn't get an answer like -5 or, +23 or whatever. The fact that it's exactly where it should be is very, very reassuring, because I think it kind of means that even if you may not believe all of these error bars, we have done our best, but you can always question the error bars. They can't be very seriously wrong, because the values are in the range that you expect based on your theoretical expectations. So we have exceptional objects, things close to 1, things close to 0. And at the moment, I cannot tell you what is the reason why one fellow will be close to 0 and the other one near 1. Something in the progenitor history of these black holes has made the difference. It's a huge factor, factor of 10 or more in angular momentum between these two objects. And I don't know really what was the history. This is for experts in stellar evolution to figure out why this one should be so different from that. We will get more spins in the future. And what I'm most excited about is we will use these measurements combined with the iron line method to calibrate the iron line. Because the iron line has got, its own uncertainties. Cross comparison of two methods, I think, will make both methods better. And what I like about the iron line method is that this is the only method that can be applied to supermassive black holes. Our method works only for stellar mass black holes. So I'm very hopeful that we can soon figure out how to do the iron line correctly, apply it to supermassive black holes, and then, we can really, as I said, do galaxy evolution and things like that. There is one theoretical issue. Let me not dwell on this too much. I'm a theorist. I should focus on theory, but I thought this audience might prefer the observations more. Everything finally depends on the model, right? The data you can collect with all the precision you want. And the data show great internal consistency. I showed you 403 spectra all give the same answer. So, there is something very, very nice and solid, but finally there's a model. And the model we are using is this model, Novikov-Thorne model, which tells you how intensity varies with radius. Large parts of this model are very robust. I told you there's no alpha, it's all just G, C, and things like that. But there are some assumptions. And now it's time to mention that. There is one very crucial assumption in this model, a so-called no torque boundary condition. Because if you ask, why does this intensity go up and then come to 0 at the ISCO? Why doesn't it keep on going up until it hits the ISCO? This is a result of this no torque boundary condition. It's an assumption that was introduced by Shakura and Sunyaev, borrowed by Novikov and Thorne, and everybody who does accretion disks always assumes this, that at the ISCO, there is no viscous stress. And as a theorist, you can convince yourself that this is okay, but still, it's an assumption. You need to test it. And fortunately, today we are in a position to test this because we can simulate accretion disks where you don't have to make any assumptions. You just let the computer do whatever it wants. You just put in the conservation laws of physics, put a black hole, put some gas, and let it go and see what it does. So I will just show you numerical results. This is published in this paper by Kulkarni et al. So here are 4 simulations. This is just, I'm not showing you the simulation themselves, just the final result. 4 spin values. The dashed line is what Novikov and Thorne tell you the flux versus radius is supposed to look like. The solid line is what we are getting from the simulation. The difference between these two, Novikov and Thorne is an analytical model which makes a specific assumption about the boundary condition at the ISCO. The solid line is from the simulation, completely numerical, but no assumptions. It doesn't follow exactly, but I hope you are kind of encouraged. I am terribly encouraged that it looks a lot like the model. Clearly, the intensity is not 0 inside the ISCO. There is some radiation, but the peak is pretty much where the model says, and very clearly the intensity falls as you reach the ISCO and get levels off in the center. So now, what you can do is you can take these simulation results and you can now estimate how much error we are making. This is a systematic error, right? We have a model. The model is not precisely correct. It's got some deviations. But since we know from the simulations what the deviations are, you can ask, what is the error? So I won't show you the numerical results. The bottom line is the error coming from this, the deviations in the model are no more than the error bars that we have got here in the measurements. Okay? So the good news is we have a small systematic error because the model is not precise, but it is small. Right now, observational errors are more serious than the theoretical model errors. At the moment, the theory is not stopping the game. It's just the fact that the observations are still limited and we can't do better than a certain amount. So I would say these values are still looking good. If you want, you can double the error bars, just to be safe. But I would be pretty confident that this guy is a low spin, this guy is a high spin, and these are in-between spin. That kind of ordering, I believe, one can believe. So I better stop at this point. 5 minutes, I will stop. I said I will mention one quasi-answer that the measurements have given us. So let me remind you. Black hole spin, as we said, is the second hair. We are all sure that it's a very important hair. It's going to have big effects everywhere in astrophysics. And the biggest effect everybody expects is that relativistic jets are powered by spinning black holes. And so if you've got a variety of black holes, the more rapidly spinning guy will have a big, powerful jet, and the non-spinning guy maybe won't have a jet at all, or a weak jet, or something. So now we've got 9 black hole spin measurements. We can go and ask, what do we know about jets in these objects? Now, all these black hole X-ray binaries, they all produce to varying degrees radio emission at various times, okay? And the radio emission is invariably associated with jet ejection. So, jets are seen in several of these. Cygnus X1, for instance, has got a radio jet. It's almost always visible in radio. It's a radio source. And several of the others, the microquasar GRS 1915 is a very, very famous jet source. In fact, spectacular jets, as you know, with proper motions greater than the speed of light and things like that. So you can go and look at the radio data on these objects. And this table, the J here means that radio has been detected in this object. So every object here with a J has been detected as a radio source, and the radio can only come from a jet. Okay? I don't know whether it's a relativistic jet or not in every case. This guy definitely is relativistic. This guy is definitely relativistic. This guy is definitely relativistic. 1550. A0620, we don't know. All you know is that there is some radio flux coming. The guys without the J, we have not seen radio emission. But these are the most distant ones, right? Two of them are in LMC, and one is in M33, even further away. The other 6 are all in the galaxy, and every one of them has produced radio emission. If you want to say that radio emission means relativistic jet means rapid spin, this table is saying that that story does not work, okay? Well, you have to do something. You can say that these values are meaningless, that, we have tried hard, well done, but too bad, these numbers are no good. I think that's not right. I think the numbers are pretty reasonable. I believe these numbers, as I said, I will double the error bars, but I still believe in the ordering of these numbers. Or else you have to say that just radio emission doesn't mean relativistic jet. It just means some ejection of some sort. But whatever that ejection is, it doesn't seem to care about the black hole spin. So I would say at the moment, I am really very much split. I'm a theorist, right? For a theorist, the connection between black hole spin and relativistic jets is extremely attractive. It's a beautiful idea. It has to be right, okay? It has to be right. But then I've got involved in this observational project with Jeff, and the data are telling me that this is not adding up, that this table is saying that maybe black hole spin has some effect on jets, but it's not the whole story. Something else is there which produces radio emission and ejection in all black hole accretion systems, regardless of the spin. I think we have to wait for more data. We have to look at the particular epochs when the radio was observed, what kind of emission, what kind of ejection. We need more data, basically. But I would say this is the first time that you actually have some real data to start testing some theoretical ideas on what black hole spin might actually do in astrophysics. it has to have an effect. It is, it's only 2 hairs. It's a second hair. It must have an effect. At the moment, the most promising connection seems to be a little bit shaky, but something else may be present. Stay tuned. I don't know the answer beyond this. So the summary is nothing. Stellar mass black holes are great fun. They've been around now for a few decades. Masses have been measured. We got masses for about 20 objects, and nearly half of them now have spin measurements. Hopefully, we'll get a good fraction of the remainder also in the next several years, maybe with some help from people here. And this is where the fun is going to be, to start looking at what is the astrophysical connection between spin and anything else that we observe from these systems. Specifically jets, but also other possible signatures of spin. Thank you.
Any questions or comments?
Okay, I have a couple of questions. The first one is a very naive one. The spin is a vector, and so it's more than just one single parameter that you have to fit.
It's a direction, right? Yes. There's an axis, so you have to define the direction of the angular momentum vector. And then the magnitude of the spin is given by this scalar quantity.
Okay.
So think of it as an angular momentum vector.
So you have to, in all this modeling, you have to assume a given direction, right?
We assume that the spin is orthogonal to the direction of the accretion disk. This is very reasonable, okay? I can go into details if you want. But we also assume that the disk is aligned with the binary. So we are assuming that there is a binary orbital angular momentum vector, there's a black hole angular momentum vector, and there's the accretion disk angular momentum vector. We are assuming that all of these are parallel.
Okay. The second one, and I finish, and I leave all the to give questions, is about, you mentioned in the biographs, but you never explicitly talk about that. It's the role of magnetic fields in modeling the accretion disks. Could you neglect them? Are you taking them into account?
You're talking specifically neutron stars or black holes?
I don't know.
Okay. So black hole itself doesn't have a magnetic field, okay? But the accretion disk will have magnetic fields inside the gas. So the simulations that I showed, I didn't show the simulation, but the results I showed, those are actually MHD simulations. So they include magnetic fields, and it's the magnetic field that gives you the viscosity and the stresses, accretion, etc. So the magnetic fields are included in the physics of the gas. But there is no permanent magnetic dipole on the black hole. That's not allowed. You can only have magnetic fields attached to the disk.
Okay, thank you.
Yeah. So maybe just to amplify on that, that's the difference from the neutron star. A neutron star can have a permanent dipole, strong magnetic field. But a black hole has only 2 hairs. If it had an extra magnetic field, it would be 3rd hair. It's not allowed. So, yeah.
Yeah, I have a question about the meaning of the very low value. Why do we expect to have a black hole with low spin or spin 0? Or let's put it another way, can we expect a black hole spinning very fast and then slowly decrease, or having burst and spin back and forth?
Yeah. So if you look at the life of one of these black holes, before it was a black hole, it was a big O star, right? And the O star was spinning. So there was some angular momentum. Then there was the collapse to the black hole. And we expect angular momentum must have been conserved. So depending on how much angular momentum the star had, you will get some spin for your black hole. So when it is born, it will have some spin. But then there is accretion. So while the accretion is happening, accretion is bringing in angular momentum with this gas. And you're constantly adding angular momentum and mass to the black hole. So the mass will go up. Angular momentum will also go up as a function of time. So in principle, most of these systems, we expect they are born, and then they are increasing their spin slowly. But you can go and estimate how much extra spin does it accumulate from the accretion. Most of these systems don't accumulate very much. So by and large, the spin values that we are measuring, they represent the initial birth spin of the black holes, and then maybe a 10% change afterwards. But not a big, it's not gone from 0 to 1. There's not enough time or enough mass. This is for the stellar mass black holes. For supermassive black holes, the story is quite different. Those systems, those black holes accrete so much gas, in principle, they can change their spin through accretion by a large factor. So it's an interesting problem. But here, I think mostly what we are measuring are the birth spin plus or minus 0.1. And you are asking whether they can go down. Very unlikely. If you're going extremely fast, you might actually go down a little bit. But all of these systems, I would say, they are only be going up as a function of time, not likely to go down.
Then we have time for one more question.
The last summary, the last sentence you stressed, the one in which you said that because there is no correlation between the spin number and the presence of jets, it's very challenging, very interesting, very intriguing, I don't know how to say. And so if everything you have said could be translated into more massive black holes, that could be a real problem in order to interpreting all these high energy phenomena we are looking at.
Absolutely. This is why I am very worried by this result. I'm hoping that we will still find a connection with spin in some fashion. Maybe the answer is all black holes will produce ejections, but the most highly relativistic ejections come only with maximum spin. Maybe there is some connection like that. The data are not supporting the statement right now, but something like that is going to be needed. But I agree with you, especially when you go to the supermassive black holes, this whole, there's the whole blazar phenomena, the radio loud, radio quiet, dichotomy. There's just enormous amount of stuff there, which is going to be problematic if we give up the idea of black hole spin. So I'm just giving you data here. I'm presenting it, but I don't want to give you a bottom line at the moment, okay? So I'm just saying it's intriguing. You said it's very intriguing. Absolutely, it's intriguing. But I don't know what it means yet.
Okay, can we thank Ramesh one more time? Don't forget we have coffee at 12 o'clock in the cafeteria.